All right, so we're moving on to another topic, one that you have read about in Heart of Mathematics, and one that I want to kind of delve into a little bit more deeply. This, to me, I wish that someone would have spent more time explaining this stuff to me when I was a math major, or even just, sort of acutely interested in math. I think that this would have been a very good hook for me, and it would have also instructed my mind in terms of how sometimes abstract mathematics, or mathematics that appears to be worthless on the front end, like purely abstract mathematics that looks like there's no way that this is ever going to be applicable, ends up being exceedingly applicable way after the fact, even after people are dead that invented it. Yeah. And this is one of those situations for sure. By the way, I think the schedule was really kind of speeding along. I backed off. There was like 7.4 through 7.6, those sections in Heart of Mathematics. I think I put an assignment that isn't necessarily due until like next Monday or something like that, okay? Just to make sure I'm keeping you apprised of that. But let's talk about number theory, and that number theory will form the basis of a cryptographic scheme, which is one of the most important in all of cybersecurity, called RSA cryptography. Okay, this is one of the first public key crypto systems, and we'll figure out what that means later on. But essentially what it means is you can publish a bit of information for all the world to see, and they can take that bit of information to encrypt a message they want to send to you. So I publish something that everybody can see, even like enemies of the state, okay? People that are wicked. Everybody can see it. You can encrypt a message to me and no one can decrypt it. Not even the person who encrypted it. Does that make sense? No one can decrypt it except me. I'm the only one who has the ability to decrypt that message. That might sound surprising to you. You're like, I just encrypted that message with that public piece of information. Why would I not then be able to decrypt it? Well, we'll see why that happens to be the case. Okay, there's some interesting history behind this as well that we'll talk about. Okay, so what is number theory? Well, it's the study of integers and all properties that they might have. And in particular, there's a lot of focus given to primes, because primes, after all, are kind of the building blocks of integers, yes? So everything that we're talking about in this part of the course is an integer, okay? We're not talking about pi or the square root of 2. We're talking about integers, okay? Now, I will say that this is considered pure math, and for a long time it was considered to be pure math of the most abstract, worthless variety. But nowadays, there's just a vast number of applications in computer science and elsewhere, right? Especially cybersecurity, okay? And my goal for us is to explain everything necessary for us to understand the RSA cryptographic scheme in full, okay? RSA, by the way, stands for Rivest, Shamir, and Adelman. Those were the three mathematicians / theoretical computer scientists that came up with the RSA crypto system, okay? That was talked about in the Heart of Mathematics, yeah? So here's the first part. There's actually going to be 3 parts. The first part is just us familiarizing ourselves with kind of the typical sort of thing that we do with integer study. That is in the study of numbers, number theory. And by the way, there's an entire class devoted to this subject that goes a lot deeper than we're going to go. And there is just some unbelievably interesting things in the realm of number theory. I am not a number theorist, but I have gotten obsessed with number theory at various points in times in my career, and And actually, I have a little expository paper that Dr. Fry and I just wrote, actually, that has to do with divisibility tests. And I might have you actually read that once we finish Heart of Mathematics. And it will, I think it will hopefully intrigue you, okay? So let's talk about divisibility and modular arithmetic. A lot of you might have seen this sort of thing in the past, but that's okay. So divisibility, okay? If A and B are integers, and A is going to be the thing we divide by. Therefore, we want A to not be 0, okay? Okay. A and B are integers, A different from 0, then we say that A divides B if there exists an integer C such that B is equal to A times C. Now that might look like a lot of letters and confusion, but essentially what A divides B means is that B is a multiple of A, yes? B is a multiple, an integer multiple of A. We're not talking about anything but integers right now. At this point in the course, it is heresy to talk about anything other than integers, yes? Okay, we're only talking about integers. So A divides B means that B is a multiple of A, yes? So you can kind of repeat that in your mind. There's some notation we use here is this A/B thing, okay? A/B. And the way we say this is A divides B. Okay, therefore, what do you think this means? Yeah, this is A doesn't divide B, okay? And by doesn't divide, I mean perfectly divide, yes? Okay. So it might be obvious to you, but A divides B if and only if B over A is an integer, yes? Okay, so that means that B over A is equal to some C, which happens to be an integer, yes? We have all this nice notation we can take advantage of now, which by the way means that B is equal to AC, just like we had right up there, yeah? Okay, so there's lots of ways to kind of say this same thing. So divisibility here means perfect divisibility, okay? Of course, I can always take 8 and divide it by 3, and we can say that 8 is divisible by 3 because I am able to divide 8 by 3, but it is not perfectly divisible by 3, yes? That's what we mean here. Any questions on this? We're going to use. Yeah.
So why can't A be 0?
Why can't A be 0? Well, why don't you think A can be 0?
Well, so if A was 0, then B over A wouldn't make sense, right?
That wouldn't make sense, right?
Yeah.
And moreover, if you're trying to see how many times A goes into B, where B is something other than 0, okay?
Yeah.
What would you be able to pull that off?
No.
I mean, you would say, well, okay, B is 7, A is 0. How many times does 0 go into 7? Well, okay, I'm going to make one group of 0 and another group of 0 and another group of 0. Am I getting any closer to 7? No, right? In some sense, you can kind of see why the answer would be something like infinity, right? But just to avoid crazy things like that, we don't divide by 0.
Well, because, right, like if you said like, you could say, I was thinking you could say like 0 divides 0 because 0 equals A times C for, like there exists an integer C such that 0 equals 0 times C.
Yeah. So the problem is, actually, it's probably a number theorist might actually get upset with just simple existence of an integer. What they might say is not just there exists, but they would say there exists, what do you think?
Exactly 1.
Yeah, a unique, right? Remember, there exists a unique, that exclamation point means unique. They might be interested in there being a unique integer. And of course, it is true, as John was saying, that 0 is equal to 0 times c, yeah? But what's the problem with that multiple in this equation? C could literally be anything, yes? So there's not a unique answer to the division problem. Does that make sense? We would want a unique answer to the integer division problem. So that's why we don't permit a being 0. Does that kind of help, John?
Yeah, I guess. Yeah, that helps.
Okay. Uniqueness. There needs to be one answer to the B over A situation. Okay. Here are some properties. A, B, and C are integers. A is different from 0 since A is going to be the thing we divide by. If A divides B and A divides C, that means that B is a multiple of A, but also C is a multiple of A. Does that make sense? Yeah? Then B plus C is also going to be a multiple of A. Okay? Another way to say it, if A divides B, this means that B is a multiple of A, but also it means that A is a factor of B. Okay? A is a factor of B. So like there are multiple ways to say this. A is a factor of B, A is a factor of C. Therefore, if I add B and C together, A will also be a factor of B plus C. That's what this little statement is saying. Okay? The second item, if A is a factor of B, then isn't it clear that A is going to be a factor of any multiple of B? Any integer multiple of B? Yes? Okay? So, I mean, like here's an example for, well, actually, we'll look at these examples here at the bottom, but is it clear to you that if A is a factor of B, then A will be a factor of any multiple of B also? Yeah? If A is a factor of B and B is a factor of C, then A is going to be a factor of C. Yes? That's oftentimes referred to as the transitive property of divisibility. Yeah? Okay, so like A is a factor of B, which means if I wrote out B's factorization, you would see A in there. Then of course, B would be a factor of C. I would see A within there as well. So A would have to be a factor of C. Here's examples of all three of these statements. 2 divides 6, right? And 2 divides 8. Therefore, 2 will also divide 6 plus 8, which happens to be 14. 2 divides 6. So 2 divides any multiple of 6. In particular, it divides 4 times 6, which is 24. Okay. Lastly, 2 divides 6 and 6 divides 24. Therefore, 2 divides 24. Okay. Mm-hmm. Yeah, they're sort of logic, yes. Okay. Any questions on that? Here's a little corollary, right? Remember, corollary means something that follows immediately from the previous slide, if you just kind of think about it, yeah? From the previous information, if we just think about it. A, B, and C are integers. A is the divisor, and therefore we don't want it to be 0. If A divides B and A divides C, then A will divide any integer combination of B and C. Because after all, think about it. If A divides B, then A is going to divide any multiple of B, correct? And if A divides C, then what? A will divide any multiple of C, yes? But if A divides this guy and that guy, then it will also divide the sum of those two guys, yes? So I can take any multiple of B and C and add them together, and if A divided B and C, it will divide that combination of B and C. This is oftentimes referred to as an integer combination of B and C, okay? That's an integer combination of B and C. So for instance, 2 divides 6 and 2 divides 8, correct? Therefore, 2 will divide any multiple of 6 plus any multiple of 8. So in particular, I could take 6 times 3, which is 18, and add that to 8 times -4, which is -32. Okay? 18 minus 32 is -14. And does 2 divide -14? It surely does. Okay? So that follows immediately from the previous 3 properties, yes? I had one of the properties that says if A divided something, then it will divide any multiple of it. Okay? And we also had something that said if A divides one thing and A divides another thing, then A will divide the sum. And essentially, we've just combined those ideas to get this one. Yeah? Okay, so if A divides one integer and A divides another integer, then it will divide any integer combination of those two things. That's kind of interesting. Okay? Any questions on that? Please ask. Well, let's talk about the division algorithm. Okay, this is important, and actually this comes from Euclid. This was one of the things that was kind of a highlighted feature in Euclid's Elements. And this was the thing that kind of provided the transition between geometric facts to number theoretic facts. Euclid delved into the area of number theory. Remember, we even looked at one of his proofs that had to do with number theory. Which one was that? Do you remember? We proved that Euclid, we showed Euclid's proof of the Pythagorean theorem, but there was another thing that Euclid proved. Infinitely many primes. He showed that there was an infinitude of primes, yes? And one thing that he really made rigorous for the first time was this thing called the division algorithm, okay? So here's how it goes. If A is an integer, and D is a positive integer, okay, then there, okay, and I can't emphasize it, like I'm only talking about a positive integer this time, okay? That just, that makes the computation a little bit easier to deal with. Then there are unique integers Q and R with R smaller than D. By the way, D is the divisor. It's the thing we're dividing by, okay? Such that A is equal to DQ plus R. Now, what that means is you've basically seen how many times D goes into A, yes? And kind of Q is that answer. That's the quotient. And then you have this remainder that you call R. So D is the divisor, A is the dividend, Q is the quotient, and R is the remainder. And computer scientists love to, rather than like using Q and R, they'll actually call this A div D and A mod D, and they use this boldface type. And there's actually, if you go and take C++, and you use like the division symbol in C++, it will give you this, the quotient. It will actually do integer division. And if you use the % sign in C++, that will actually give you the remainder, R, okay? So there are operations in programming language C++ that actually gives you these two things quickly. Okay, the fact that C++ devoted specific symbols to these things indicates that these are important, right? Okay, and we'll talk about examples of what's going on with the division algorithm here, okay, in just a second. So there are unique quotient and remainders. If you hand me a number, which is the dividend, and a positive divisor, I can find these unique integers Q and R that form this little equation. Okay? Let's look at an example though. Find Q and R. Now remember, so A is equal to DQ plus R, where R is equal to or greater than 0. It's going to be equal to 0 if I have perfect divisibility, correct? And the remainder is smaller than the divisor. What? Let me ask you a question. Why would I require that the remainder be smaller than the divisor? What's that? Right, because because if the remainder was bigger than the divisor, that means I didn't go in enough times. Does that make sense? It was like, that was stupid. I should have gone in more times. Does that make sense? Okay, so what I want you to do is work on these two problems with those that are around you right now. Okay, find the Q and R that are guaranteed by the division algorithm. Okay. Okay. So how many times does 5 go into 14? I'm not trying to insult your intelligence here. 2. That's the quotient in this case. So 14 is equal to 5 times 2. That's the quotient. And then what's the remainder? 4. So in other words, Q is equal to 2 and R is equal to 4. Now, the divisor always has to be positive. So, and by the way, how could I have the gall to always require that the divisor is positive? Well, because I can always make it happen, you understand? If I wanted to divide a positive number by a negative number, then I could just swap the roles and the answer would be the same. Does that make sense? Because a positive divided by, the answer is just going to be negative anyways, yes? What if they're both negative? Right? It's going to be the same if I just flop them both to positives anyways. Okay? Now this one's weird. You might be tempted to think that negative 14, so I'm dividing negative 14 by 5. Okay? Now, how many times does 5 go into negative 14? Negative 2, but the problem is if I wrote negative 2 here, I would have negative 2 and I would have what kind of remainder? Right? Negative 4 would be the remainder. Therefore, I need to actually back up one more. So what do I get? Negative 3, that gets me below negative 14. And so what's the remainder? Plus 1. So in this case, Q is equal to negative 3 and R is equal to 1. Now, here's the thing. You might say, how could I quickly get the quotient? How could I quickly get the quotient? So like, think about this first one right here. You would go 14 divided by 5, which is basically 2.8. Does that make sense? Yeah? And then what you could do is you could do this thing called take the floor of this thing. Take the floor. The floor means the largest integer that is less than this. Does that make sense? So the floor is like, you go like this, and that means you just get rid of like the fractional part. You kind of drop down to the integer right before this. So what would you get if I took the floor of this? That's what this notation means. You would get 2, which by the way is Q. Now here's the thing. The same thing works here. I promise. Because look, if I went negative 14 and I divided that by 5, what is that? That would be negative 2.8. And if I take the floor of this, that means I go back to the next integer. Yes, backwards to the next integer on the timeline. And what would that be? -3, which happens to be the quotient, right? So there's a consistency here, yes? Turns out that if you take the dividend over the divisor and take the floor every time, you will get the quotient. And then you can kind of figure out what the remainder is after that, yeah? But do you guys see how the negative divisors are a little bit, or sorry, negative dividends are a little bit strange, right? They kind of complicate matters, but we figured it out, right? Okay. Any questions on that? Okay. I'm trying to remember, didn't they talk about the floor operation in the Heart of Mathematics at some point? I feel like they may have actually mentioned it, like kind of going down to the next integer. There's also the ceiling operation. The ceiling operation moves you up to the next integer, yes? So like the floor of pi would be 3, and the ceiling of pi would be 4, okay? So yeah, here's this, right, okay. Let's talk about modular arithmetic. So this is arithmetic modulo M, okay? Sometimes this is referred to as clock arithmetic, okay? Clock arithmetic. What time is it? 30 hours after 3 o'clock. Now, again, I'm sort of ignoring AM and PM here, okay? I'm ignoring AM and PM. I don't want to give it away. I accidentally just revealed something, but okay. 30 hours after 3 o'clock, what time is it? 9 o'clock. You guys just instantly did that because you realize every iteration of 12, I'm going to be back to 3 o'clock again, yes? And you say, okay, there's going to be 2 iterations of 12, and then I have to go 6 beyond that, yeah? And that puts me at 9 o'clock on the clock, okay? So 3 plus 30, basically what we're doing is 3 plus 12, and you know that 12 simply wraps you back to 3, and then we end up at 9 o'clock is the essence of what's happening. Now, it turns out that this clock arithmetic is at the heart of doing some pretty interesting number theory, okay? Some number theoretic considerations. This is really addition modulo 12, okay? Every 12, you're kind of back to the beginning. You call that addition modulo 12 or modular arithmetic, or modular addition. We're ignoring AMs and PMs here, okay? Does this make sense? Hopefully. Just wrapping around this thing, okay? What we really did, now remember, we had that bold-faced mod thing, yes? Remember back on the previous slide, or a couple slides back when we introduced the division algorithm, mod meant remainder. Does that make sense? Mod actually meant the remainder. And I'm telling you, that's what we did here. We took 3 plus 30, and we took the remainder of that upon division by 12. Do you see? If you take 33 and you divide it by 12, what do you get? Yeah, 2 remainder 9. And since mod is specifically obsessed with the remainder part of that, yeah, because this is going to be the remainder, right? Then that remainder is 9, yes, in this case, right? And this right here, that 12 right there, that's the divisor. And this guy right here, 3 plus 30, that was the A, right? The thing that we were dividing into, the dividend, okay? Okay? Does that make sense? Okay? Here are some facts. Facts. Okay? That probably aren't going to be all that surprising to you. So first of all, we start with the basic assumption that A mod M and B mod M. Okay, now mod means the remainder upon division by M. Yes? A mod, it will, not, okay, so like the remainder of A, if I were to divide by M, if that's equal to the remainder of b upon division by m, does that mean that a and b are the same, by the way? Certainly not, right? Can you think of two things? For instance, like 15 mod m is the same thing as, I don't know, I mean, or sorry, mod m, hang on a second, I meant to say mod 12. Okay, 15 mod 12. Can you think of something else? What is the remainder of 15 upon division by 12? 3. Can you think of another number that has remainder 3 upon division by 12? Well, 3. 27. Yeah, you just add 12. Exactly right. You just add 12 any number of times, and you'll end up with something that has the same remainder. By the way, I could also subtract 12. Yeah. So, I mean, this is the same thing as 3 mod 12, which, by the way, is the same thing as, negative 9 mod 12. And you might say to yourself, what? Yeah. Negative 9 mod 12. Well, I'm telling you, if you divide negative 9 by 12, think about it. If you divide negative 9 by 12, what are you going to get? Remember, we take the floor, and this will be the quotient, right? That will be the quotient of this thing. What do you get if you take negative 9 and divide it by 12? That's like negative 3/4, and I take the floor. What's that? Negative 1. Do you see? So we see that negative 9 is equal to 12. I'm dividing by 12. 12 times negative 1 plus what? Plus 3. And 3 is the remainder. Yes? Right? So all of these things are have remainder 3. Yeah? All of these things have remainder 3. So A mod M equaling B mod M, that doesn't mean A and B are the same number. It just means they have the same remainder upon division by M. Yes? So what I'm assuming below is that A mod M is equal to B mod M, and that C mod M is equal to D mod M. That means A and B have the same remainder upon division by M, and so do C and D. Okay, but you know, it might be a different remainder for C and D, okay, than it was for A and B. What do these imply? Well, it implies that if I were to take A plus C and take it mod M, then I will get the same thing as if I took B plus D mod M. Okay? Yeah? We'll look at some examples here pretty soon, but just wanted to point that out. Moreover, I can multiply A with C and B with D, and I will get the same thing mod M. Okay? Do you see that this is kind of acting like equals in some way? I know there's the awkward mod M there, but if you just ignored the mod M part for a minute, this would just be stupid to us. Do you understand? Of course, if A was B and C was D, then A plus C, of course, would be B plus D. Do you see what I'm saying? Duh, right? But the modular arithmetic gives us a little bit more flexibility with these sorts of things. And A times C, of course, would be the same thing as B times D. Okay? And this right here, number 3, is actually one of the most important facts listed on this page. Okay, if A and B have the same remainder, then if I take the difference between A and B, that will be divisible by M, which means the remainder is 0. Doesn't that make sense? I mean, think about it. If I take two numbers that have the same remainder upon division by M, and I subtract them, what's going to happen to the remainders? They have the same remainder, so what's going to happen to the remainders? They will cancel. And what will be left is something that is perfectly divisible by M. Yeah? So for instance, you know, 15, or let me just say 15 mod 12 is equal to negative 9 mod 12, right? So what this is saying is 15 minus negative 9 mod 12 is what? It should be 0. Is that true? Well, what's 15 minus 9 for crying out loud? 24. What's the remainder upon division by 12? A 0. What is happening when I take that difference is the remainder completely blitzes itself, yes? Because there was the same remainder for each one of those things, namely 3 in this case, okay? So this third one right here is exceedingly important. If A and B are the same modulo M, oh, by the way, I'm annoyed by the fact that I scribbled all these out for the sake of illustration. Okay, but I'm just saying, I was just trying to point out the fact that these are not like they should be sort of obvious if you think about it in terms of equals. Okay, so if A minus B mod M is 0, that just simply means the remainder is canceled and therefore M divides that difference. Yeah, perfectly, no remainder. This last fact is a very important equivalence. A mod M equal B mod M if and only if A minus B mod M is equal to 0. Of course, if these were just equals, wouldn't it be obvious anyways? Like A is equal to B if and only if what? A minus B is 0, yes? Okay, but it's just a little bit different with this. Okay, A mod M is equal to B mod M if and only if A minus B mod M is 0, if and only if the thing we're dividing by, the so-called modulus, divides A minus B. Okay, the reason I'm using M is to remind you of modulo, modulus, modular. All of these terms are kind of used interchangeably. I have this example at the bottom that's not unlike the one we just did. Is it clear to you that 13 mod 3 is the same as 7 mod 3? What's the remainder for each one of those? 1, yes? Those are both have remainder 1 upon division by 3. If I take 13 minus 7 mod 3, you get 0 because the remainders cancel. Okay, 13 minus 7 is 6. I take that mod 3, I get 0. And of course, 3 divides 13 minus 7, right? So that equivalence is an important one. Okay? Okay, so we're going to kind of build on this modular arithmetic next Monday. But on Friday, we have an exciting presentation on Bernoulli. Is that right? Yes. Okay.